Hello there and welcome to a new series of PYQ questions. In these videos we'll be covering PYQ questions from the examinations for the examination point of view, and we'll be explaining them quickly and we'll be going through all questions for most modules. So let's get started. So the first question says the following memory units are specified by the number of words times the numbers of bits per word. Okay, how many address lines and input output data lines are needed in each case? So it says part A has 2k into 16, 64k into 8, 16m into 32 and 4g into 64. So what you need to understand over here is the values of k, m, g. Fine, these are kilobytes, megabytes and gigabytes. Okay, so k will be 1024, m will be 1024 times 1024 and g will be 1024 3 times multiplied. Okay, so for that what we are going to do is first we are going to convert these into powers. Okay, so since we have 2 already, okay, 2 into 1024 will give us 2048, and then we can convert that to the power of 11. Fine, so 2 to the power of 11 into 16, and from this sort of expression you can see that 2 power 11. Okay, so whatever the power is the equal to the address lines. Okay, in terms of understanding the statement, whatever the power is equal to the address lines, and the multiplier, it says number of bits per word, so 16 bits per word, hence for each bit we need a data line, so 16 data lines per word. Fine, then coming to the part B, 64k, so 64 into 1024 we will get it will be equal to 2 power 16. You can find this through basic simple mathematical simplification. Okay, so 2 power n equals to 64 into 1024, and once you find the power, that will become the number of address lines. This is a mistake over here, it is supposed to be 8 because it is 64 into 8, hence we will have 8 data lines for 8 bits. Fine, over here we have m, so 16 into 1024 multiplied by 1024, that will give you some value, and you are supposed to find the 2 power n, which is 24 in this case. Finding the address lines, 24 is the same. Okay, so the power is the number of address lines, and you already have the data lines given, because number of bits per word, for each bit you will have a data line, so 32 data lines. Similarly for g, that means gigabytes, 4 into the multiple of 1024 3 times, you will find the power n, the n will be the address lines and 64 will be the data lines. In the next question we have how many 128 into 8 memory chips are needed to provide a memory capacity of 4096 into 16. So we are given a memory capacity that is required, and we have the memory capacity of the chips that we have. Okay, so in order to find out how many of these chips are needed, we can just find the ratio. So 4096 into 16, okay, whatever the answer is, divided by 128 into 8 will give you 64 chips. It's a very basic calculation. All you need to do is find the ratio, okay, of the sizes, thus it will give you the number of smaller chips that you need to get to the required memory capacity. In this question we are given with a statement and we have to implement the block diagram of the hardware. So we have two controls, y and t2, both are 1 because there is no bar or dash written over there. That means y1 and t1 will cause the following statements to be executed. So y and t2 y and t2 are both ANDed, okay, using an AND gate, and they are loaded onto the registers. We need to look at the statement now. R1 is transferred to R2 and R2 is transferred to R1. So R1 we will transfer it to R2. We are supposed to write n bits because we do not have the size specified, hence we will say that the size of the R1 data register and R2 is n, and R2 has an output over here, but it also has its output going to R1 as input. Fine, this is also n bits, and both the conditions can be carried out, R1 stored in R2 and R2 goes to R1. We do need to remember to add a clock to it because both the instructions are being carried out at the same time at a given condition, hence the clock cycle has to be added to it to show the clock transition, a single clock transition for carrying out both the tasks. This question says that the outputs of 4 registers R0, 1, 2 and 3 are connected through 4:1 line multiplexers to the inputs of the 5th register R5. Each register is 8-bit long. The required transfers are dictated by 4 timing signals, T0 all the way to T4. T3. sorry, it's not clear. So T0, T1, T2 and T3 cause the following outputs. R0 is transferred, R1 is transferred to R5, R2 to R5 and R3 to R5. The timing variables are mutually exclusive, which means that only one variable is equal to 1 at any given time. Hence T0, 1, 2, 3, any one of them is equal to 1 and we cannot have more than one. This is similar to the encoder that we studied, and while the other three are equal to 0. Draw the block diagram showing the hardware implementation of the register transfer. Include the connections necessary for the timing variables to the selection inputs of the multiplexer and the load input of the register R5. So the load of the R5 will be connected to the ORing of all the timing signals, because at either statement, whether it's all 0, any if T0 is 1 or T1 is equal to 1 or T2 is equal to 1 or T3 is equal to 1, at any of them the load has to be 1, otherwise you cannot write data onto R5. Hence there will be an OR gate and it will be connected to R5, so that the whatever timing signal has the value of 1 is transferred. Now we have R0 to R3, they are 8 bits each as mentioned, so you have to mention 8. We will use a multiplexer. Now why are we using a multiplexer? Because we have 4 different registers and we need to transfer any one of them to the R5, and that is the use of a mux, where multiple lines are transferred into a single line. Any one is transferred into a single line. Again, the size is 8 bits. We have 2 selection lines in a mux because this is a 2 power n, which is 4 lines, so n is 2, hence 2 selection lines. Now to decide the variables of the selection line, which timing controls are supposed to be given, we will be drawing a truth table for that. We have T0, T1, T2, T3. They're either all 0 or T0 is 1, T1 is 1, T2 is 1 or T3 is 1, giving the remaining as 0. This causes the following patterns in the selection lines as well as in the loading. At the initial stage the load is 0 and both selection lines are invalid, because 0, that means we do not have any selection line going into the selections. Since we have 2 selection lines, we'll be having 4 different patterns, 0, 0, 0, 1, 1, 0, 1, 1. We can see that S1 is 1 in 2 different places. It's either because of T2 or T3, and S0 has 1 either because of T1 or because of T3. So the timing signals responsible for the controls will be T2, T3 and T1. We have T2 and T1 that are ORed together, T2 and T3 ORed together for S1, hence S1 will be the ORing of T2 and T3, and S0 will be the ORing of T1 and T3. So in order to determine which the signal selections and the timing lines, you have to draw the truth table, and accordingly you have to find out the variables for each. So S1, where S1 is 1, which variables are causing S1 to become 1. This will help you create the Boolean expression, and you can form the logic diagram using the gates. You can also see that the load is 1 at each of the t values. Hence there is ORing between all 4 timing signals, which is why we used an OR gate and loaded it to R5. In the next question, we are asked to represent the following conditional control statement by 2 register transfer statements with control functions. So if P equals to 1, then R2 is transferred to R1, else if Q equals to 1, then R3 is transferred to R1. So we have register R1, R2 and R3. We are having transfers that are being made based on a condition. So when P is 1, we have transferred R2 to R1, else if Q is 1, that means if P is not 1, that means P is set to 0. If P is 0 and Q is 1, then we have R3 set to R1. So once you try to understand the statement this way, you can easily find the answer, which is when P is 1, R2 is transferred to R1, P0, Q1, then R3 transferred to R1. These are pretty easy marks. It's just the simple understanding of the statement. Now the next diagram is draw a bus system similar to this must have been a question, so there it has to be similar to the bus diagram given, but use 3 state buffers and a decoder instead of multiplexers. So in this bus system we are told that there is as we can see, since the diagram is not given, we can just see from the answer that there have been 4 registers CD, A, B, C, D, and we have decoder. It asks to use a decoder and tri-state buffer. So whenever we use a tri-state buffer, you need a decoder along with it to set the value of the tri-state buffer to either 0, 1 or high impedance, and since the registers are of 4 bits, so we'll be using 4 tri-state buffers per register. So this is a more simplified way of making the expression. Since over here there is overlapping of lines which might cause confusion, we can make the 3 tri-state buffer bus system accordingly. So you have register A connected to 4 tri-state buffers. Each of them are given the same decoder line. So if the selection is 0 0, then each of the tri-state buffer will be having one value transferring, and hence it will allow the A bit transfer. Similarly, in the second row of tri-state buffers, we have the B bits. The register B is connected, and we give them the same line, the second line of the decoder in each of them, and so on. Third one has the third line of the decoder, and it is for C, and the next one is for D. You can make them either way, and we have the final output, which is the 4-line common bus, and this represents how you can make the bus system using tri-state buffer and a decoder. The next question is, a digital computer has a common bus system for 16 registers of 32 bits each. The bus is constructed with multiplexers. So here we need to find out the number of selection inputs and basically the details for a common bus system. So how many selection inputs are there in each multiplexer? The important thing to notice is that the bus system has 16 registers and 32 bits each. If you remember, we studied in the chapter of mux that in our syllabus the classification of mux is only up to 16 bits. So we have 2, 4, 8, 16. We do not go up to 32. There are 32-bit mux in practicality, but our syllabus does not allow them. Hence we have the answer that we have how many selection inputs in each mux, what is the size of the multiplexer needed, and how many multiplexers are needed. So in a bus system, the number of registers is equal to the number of bus, but since each register has 32 bits, we will be using 2 mux per register. Okay, so 16 bit for one mux, 16 bit for the other, which will cause in total of 32 bits. Okay, so that means 16 registers means 16 mux, but since 2 mux are used for each register, we have a total of 32 multiplexers, one for each bit of the register. Okay, so this could either be one for each bit, or we have one for 16 bits of a register. Okay, and then we have 16:1 multiplexer is used, and we can calculate selection lines accordingly because it is 16 registers, and hence we will have 4 selection lines per register. This is calculated from 2 power n, 16 equals 2 power n, and that will give you 4 selection lines because you need to choose from any of the 16 registers. Remember this, the selection lines is not related to the multiplexer, it is related to the registers. You need to find out how many combinations of registers can be made for the selection lines. Next question is, the following transfer statements specify a memory, explain the memory operation in each case. These are basic memory operations that we have performed throughout in the module for memory operations. The memory address is transferred to R2, hence read memory word. So whatever is stored in the memory at AR is stored into R2. Here it is, and over here whatever is in register 3 is stored at the memory address of AR. Write content of R3 into the memory word specified by address AR. Finally we have R5 memory address. Okay, so whatever is stored, the word the content that is stored at R5 is in the memory address is stored in R5 content register. So since the register is as you can see over here, since R5 is already a register and you are making the content of its the content of R5 at the memory address is being put into R5 again. Since R5 is already a register, but you're taking its memory address and putting the data from there again, so you destroy the previous value and you put it again into the register. Draw the block diagram for the hardware that implements the following statements. X plus YZ is the condition, and we have AR plus BR stored back into AR. So update the value of AR by adding BR to AR, where AR and BR are 2 n-bit registers and X, Y and Z are control variables. So we have to include the logic gates and the control function. The remember point tells us that the plus symbol denotes an OR operation in the control, while as in the memory it is the arithmetic plus. So we need to make sure to see which symbol is being used. We have the register BR and AR set. BR is here, AR is over here. They are n-bit. Since we are adding the data, whatever it is being updated to AR, we will have an adder for adding the n bits. and the output goes to AR. The value of AR from the output is sent to the n-bit adder along with BR as A and B for adding. Again, we have to mention that it is n bits. We will connect a clock that will allow you, since we have the statement, whenever we have a statement we have to make sure we have a clock so that it shows the clock pulse or the timing at which the execution is happening. X plus YZ is the expression that we need to show. That means X is there and there is ORing between X and the output of the ANDing of Y and Z. So AND of Y and Z ORed with X will give you the load. That's it. That's all you have to draw. Basic understanding of the statement and implementation. Show the hardware that implements the following statement. Include the logic gates for the control function and a block diagram for the binary counter with a count enable input. Okay, so these are our control statements here. Okay, and the statement that is being executed is AR plus 1 is stored to AR. So this is basically an incrementer, and if we remember, incrementing and decrementing is done using a binary counter. Since we do not have the size of AR, that you will consider it as an n bit, so you'll use n bit binary counter. Connect the clock since we are using statements, and now we need the count enable, we need the control function that will be defined through the entire thing. Now we're going to look at it step by step. We have x, y, t0. That means all three of them are ANDed together. You ANDing of x, y and t0, and then we have t1, which is a separate variable. Finally you have y dash t0, y dash t2. So we take y and use the inverter to get 0, and you AND it with t2. All three outputs are then ORed, since there is plus, which is OR in terms of Boolean algebra. You finally get the control enable. The next question is design a 4-bit combinational circuit decrementer using 4 full adder circuits. So a decrementer is basically a minus 1, which is also the same as a plus 2's complement of 1. 2's complement of 1 would be 1 is represented by 0 0 0 1, and 2's complement would be 1 1 1 0, and you add 1 to it, so it will become 1 1 1 1. So a plus 1 1 1 1 will be done by a full adder. We remember full adder circuits have this is a n-bit adder. Since our A is of 4 bits and hence we have 4 full adders, we will be giving the carry as 0 since we are adding. Carry is 1 when we have to subtract, and the B bit, the B will be given as 1 in each case since we are adding 1 to A. In the general case we add A to B, here we will be adding it with 1 since we need to add A plus 1 1 1 1. Finally we'll get the output, which will be the decrementation. Consider the following register transfer statements for two 4-bit registers R1 and R2. So R1 and R2 are 4-bit registers. They have the following controls. At xt, R1 and R2 are added and updated to R1, and x0 and t1, R2 is transferred to R1. So for this one, every time that variable t equals to 1, we have either quantity 2 added to control of R1, and if x is 1, then quantity 2 is transferred to R1. If x is 0, every time that variable t is 1, we have R2 added to quantity of R1 if x is 1. So if x is 1, R2 is added to R1 and saved in R1. While x is 0, then R2 is transferred to R1, as we understood earlier. To draw this, there are a couple of things you need to keep in mind. First, we'll be drawing R1 and R2. Second, we need to see what operations are there. We have R1 and R2 added, so that we need an adder where we'll be giving R2 and R1. Okay, so we can draw a rough diagram initially, and then we can arrange the components properly. And then we also need to see that when x is 0, we get R2 transferred to R1. So we have two outputs now. It is either the summation of R2 and R1, or it is just R2, and that needs to be transferred to R1. See, so both outputs need to be transferred to R1, and either one has to be selected based on the control. This again rings the bell of using a mux. So we have either one or the second one to be implemented. We will be using a mux, which will have having either R2 directly, or it will be having R2 plus R1, the sum of the 4-bit, and it will be sent to the mux. Any one of the lines will be selected, hence we have only one selection line. This is the enable option. Do not confuse it for a selection line. It is enable 1. Enable has to be 1 in order for the mux to work, otherwise it will be switched off. The select is x. When x is 0, we have R2 over here as it is. When x is 0, we have R2 transferred. When x is 1, we have the sum transferred to R1. Remember, t is always 1, so t will act as load to R1. since both are being stored to R1, you have to remember that there has to be a loading value that will set the load of R1 to 1. If the load is not set to 1, then the data will not be saved into R1. The next question is the adder subtractor circuit. They must have shown this in a figure. Has the following values of input mod M and A B. Okay, so we need to find out the sum S0, S1, S2, S3. This is basic addition subtraction. All you have to do is when M is 0, you will be adding B to A. Okay, so A plus B. When M is 1, you will be subtracting B from A, and if there is any carry bit, you will be showing the carry bit. Subtracting B from A is the same as the complement of B plus 1. Okay, and then you'll add that to A, so you'll make its complement. For example, complement of this third value is 1 0 0 0 will have the complement 0 1 1 1, and you're going to add 1 to it. Whatever value it gives you, that number will be added to A, and hence accordingly you have to find the carry bit. You may find confusion over here, but you need to do it that way. The next question is design an arithmetic circuit with one selection variable S and two n-bit data inputs A and B. So A and B are two data inputs that are of n-bit size, and we have a selection S. The circuit generates the following arithmetic operations with the carry in. Okay, so first we look at the table. S is the selection 0 and 1, and we have four operations that are taking place. When C in is 0, we have addition of A and B. When C in is 1, we have increment of A plus 1 at S0. When S is 1, at C0 we have decrement of A, and at C1 we have subtracting A. Okay, so these are the functions that we have been given with the operations. We have to make a truth table for them, S and C in 0 0 0 1 1 0 1 1, and accordingly we can write down the operations. Finally we will implement the arithmetic circuit. If we remember, we had studied this in module 1, where we designed an arithmetic circuit using mux and full adders, and A input is given directly to the full adder. The C in is given as well. C in is the one that decides the carry. Fine, since it's given carry, it has to go to the full adder as well as to the selection lines over here, because we are having two selection lines in the mux. And then we will be giving different values of B. Either we'll be giving B directly, or we'll be giving the inverted B, or we'll be giving 1 and 0, since we also have 1 and 0. Those will be the four inputs of the mux that will go out as Y, Y0 and Y1. When they go to the full adder, the carries are joined for the full adder, and hence we'll get the output. It's a basic implementation of the arithmetic circuit. If you do not remember the arithmetic circuit, go try and look at the arithmetic circuit once. It is in module 1. The register A holds the 8-bit binary. This is the number. Determine the B operand and the logic micro operations to be performed in order to change the value of A to this and this. There are two parts. A is initially as this value, and the next value is this. What you're going to do over here is you're going to write A equals to this. You're going to leave B blank. You're going to leave some space for B, and then you're going to write the final value of A, which is 0 1 1 0 1 1 0 1. Fine, this is the first part, and then you're going to compare them. You're going to see that the initial value has 1, okay, over here, but it's a 0 here. 1 is same as it is over here. Okay, then there's the 1 over here, again similar. There's a 0 over here which became 1, so a 1 became 0, a 0 became 1, and then 1 is 0 and 1 is same as 1. So if you've seen, this is having the operation where 1 is turned to 0 and 0 is becoming 1, right? So that means we are XORing it over here. Okay, because this is selective set. This is similar to selective set, where we are setting different bits by taking B and accordingly giving the complement of A. So wherever B will be 1, it will give the complement of A. So for this we use the XOR gate, as we've studied in the arithmetic calculations. Hence we can determine the value of B. So wherever there is a changed bit in A, you'll just put 1 in B over there, the rest all will be 0, and it is XORing. Similarly, in this case, you are going to check what is happening. As you can see in this one, the zeros are being changed to 1. The ones are not changed, but the 0 is changed to 1. This can only be done using the OR gate. Why is that? Because in an OR gate, you need either one of the inputs to be 1 for the output to be 1, right? So the B bit will have 1 on those areas. It will only be 0 in the places where it does not need any bit. Okay, so if it's 0 over here and you don't need a bit, then it will be 0 here, rest all will be 1. And this way the OR gate will be giving you the same output as A equals to as A, and the zeros will be changed to 1. You can further revise this topic from the arithmetic operations on A using the B operand. The next question is, an 8-bit register contains the binary value of 100 11100. The register value after the arithmetic shift right, we have to find that, and we have to start from the initial number again. So first we have to do shift right, then we have to do shift left, arithmetic, both of them, and then we have to see whether there is an overflow. In terms of shift right, we will be, the initial value is here, okay. After arithmetic shift right, you are going to take the signed bit, you are going to push it again, so it will become 1 1, and then you'll write the remaining entire number and you'll discard the last 0. Fine, this is that. In arithmetic shift left, you are going to take the initial number and you're going to see the sign bit is going to be left, okay, as it is. So when you're going to push the number, you are going to push a 0 from this side, and then the entire number goes, and this 0 will get discarded, so it becomes 1 0 1 1 1 0 0. Now you might be saying why my answer is different. So that is an intermediate step. What we do need to remember is that in terms of arithmetic shift left, we always have to check for overflow, okay. So the first 2 bits in this are different, which means there is an overflow. Hence, although the answer is supposed to be 1 0 1 1 1 0 0 0, we are going to change the sign, as it says here. The negative number is going to be changed to positive, so it will become 0 0. Now we have the 8-bit registers AR, BR, CR and DR, and they have the following values. Determine the 8-bit values in each register after the execution of the following sequence of micro operations. We have 3 operations being performed. First, BR is added to AR, and then we have AND DR to CR, okay, and then we increment BR, and finally we have subtract CR from AR, okay. So we are going to perform each step, and at each instruction we are going to show the values of all the registers. So first we're going to add BR to AR, simple addition, fine, we'll get the AR value, and BR, CR, DR are going to remain the same, there is no change to them, only AR is changed. In second case, we are ANDing, so we'll be doing ANDing, so whenever there is 1 and 1, it will be 1, any other combination will become 0, and after ANDing CR and DR, our CR value will be as such. AR is the same, DR does not change because CR is the one that is changed, DR remains constant, and BR is incremented +1, so it becomes 0 completely because it's all ones. When you add +1, it becomes 0. Finally, at the last step, you are going to subtract CR from AR. Again, you are going to take 2's complement of CR, and then you're going to add it to AR. That is a simple way of subtracting CR from AR. You'll get AR, rest all are going to remain same because there is no change made to the rest. Thank you, and we'll be discussing further questions in the next videos.